Hi there, welcome in this new video where we solve the exam of January 2024. As you can see, the format of the exam is the same as usual. The first question deals with the four fundamental subspaces of the matrix A. In the second question, well, you have to solve a system of equations that depends on two parameters A and B. The third question is about a calibration problem, a real-life calibration problem for a grammage sensor. When you write the problem into matrix format, you end up with a least squares problem, but this time the most efficient method is not the one using the QR decomposition, as you will see later. The fourth question is also a typical question that you will find in the exams of previous years. So you're given a matrix that depends on two parameters A and B, and you have to find the values of A and B for which this matrix is positive definite. Then for given values for which this matrix A is positive definite, you have to find the factorizations. A is equal to R transpose R, one related to the pivots and one related to the eigenvalues. And for the eigenvalue decomposition, well, you do not have to go as far as you could because, well, the computations are a bit complicated. So let us start with the first question. You're given a matrix A and you have to find the four fundamental subspaces. You have to compute the rank of the matrix A and then express every column that is not in the column space as a function of the columns in the column space. As usual, try to do this by yourself and push the pause button. Well, let's start with the solution of this exercise. What we do is stack an identity matrix of dimension m. M is the number of rows next to A. And the reason we do this is to obtain a matrix E here that will collect all the elementary operations that we've done on the matrix A. So let us start. We have a first pivot 1 over here and we want to create zeros below the pivot by doing elementary row operations. The multiplier is obtained as follows. It's the element to eliminate divided by the pivot. If you do these elementary operations, this is the matrix that you obtain, this augmented matrix. Here we have our next pivot, right? And what we'll do is create a 0 below this second pivot over here. And what we'll do also is multiply the second line by -1, right? So here the multiplier, again, is the element to eliminate it, divide by the pivot. And this is what you obtain after you have performed all the elementary row operations, right? You can see here that we have a row of zeros, so we have only two non-zero pivots, right? So we know that the rank of the matrix will be 2, that's the number of pivots. And to continue, what we have to do now is to create zeros above the pivot, right? So we do this using this elementary row operation, element to eliminate divided by the pivot, and what we'll do in the end is multiply this second line by a quarter, right? And if you do this, this is the final augmented matrix that you obtain. So what we have obtained now is the matrix R, which is the row reduced echelon form of the matrix A, and as I said before, a matrix E that collects all elementary operations that have been performed. Actually, if you pre-multiply this matrix here by E, what you will have here is this matrix over here, right? And so now we can start answering the question. Remember that we've said already before that the rank of A is 2. Here we have our matrix R. It's decomposed in ER, an identity matrix of dimension. The rank of the matrix, since we have only 2 pivots, R is equal to 2. And the other matrices will be used, for instance, to obtain the null space of A. So we have only 2 pivots, so we know that the column space, which is a subspace of Rm, where m is equal to 3, the number of rows, is obtained by taking linear combinations of the columns corresponding to the pivots, right? So this is the column space of A. And to obtain the left null space of A, right, we have to go and look to the rows of the matrix E that produce a 0 row in the matrix R, right? So there is only one over here. So the null space is obtained by taking this vector, taking its transpose, and taking linear combinations. To check this, you can take this vector, transpose it, and pre-multiply A, and you will see that you have a 0 row, right? So these are subspaces of R3, of Rm, where m is equal to 3. So the sum of the dimension of the column space and of the dimension of the left null space should be 3, and this is indeed the case. Also, we know that the left null space is orthogonal to the column space. So this vector here should be orthogonal to this one and to this one. And if you do the computations, you will see that this is correct. Well, let us now have a look at the subspaces of Rn, where n is equal to 4. It's equal to the number of columns. So we have first the row space. Since we have only 2 pivots, well, we have to take linear combinations of the row of A corresponding to the pivot. So these are the 2 first rows of here, but you can also work with the rows of the matrix R. Since we have used elementary operation on the row, this is exactly the same. So this is what is indicated here. So now we need the null space of A, and for this we need to create the matrix N, which is minus F, and underneath you stack an identity matrix of dimension n minus r. N is 4, r is 2, so it's an identity matrix of dimension 2. And the null space is simply obtained by taking linear combinations of the columns of this matrix n. We are working with subspaces of Rn. N is equal to 4, and we know that the sum of the dimension of the row space and of the null space should be 4. So here it's a subspace of dimension 2, here a subspace of dimension 2. 2 plus 2 is 4, so this is indeed correct. Remember also that the null space of A is orthogonal to the row space of A, so this vector here should be orthogonal to these vectors over here. You should check this, right? And the same for this vector over here. It should be orthogonal to these vectors over here. So this leaves us with the last part of the question. So the columns that are not in the column space, really these are these columns over here, you can write them as linear combinations of the columns in the column space, which are these columns over here, and you can read this directly over here, right? So column 3 is 3 times column 1 plus 0 times column 2, whereas column 4 is 1 times column 1 plus 1 times column 2, and this again you should check, and you will see that this is indeed correct. Well, this concludes the first question of the exam. Well, let us now have a look at the second question. You have to solve this system of equation ax is equal to b, where a and b are given over here. They depend on 2 parameters a and b. So you have to find the cases where you have no solutions, an infinite number of solutions, and a unique solution. You will see that in a particular case of A and B, you'll have a so-called double infinity of solutions. This means that you have 2 arbitrary constants to describe the full solution. Well, in this particular case, you have to express the solution in full detail. So it's time to push the pause button and to try to do this exercise by yourself. Let us have a look at this second question. The first thing that we do is to stack A and B next to each other in a matrix, right? And to start the discussion on the type of solution that you have, well, you have to create zeros below the pivot. So you have to identify the pivots and then create these zeros. The first pivot is this one over here. We create zeros below the pivot using these two elementary operations. If you do the calculations, this is what you obtain. We have a second pivot over here. We create a zero over here using this elementary operation. We'll multiply the second line by -1, and this is what you obtain, right? And now we are ready to discuss, right? Well, if A is different from 3 here, we'll have a third pivot over here, and then, well, since we have 3 constraints and 4 variables, we'll have a simple infinity of solutions, right? We can see this because the dimension of the null space when A is different from 3 will be 1. So now we can start discussing the case where A is equal to 3. Well, when A is equal to 3, we have a line of zeros over here, right? If you have a line of zeros and you have something that is different from 0 over here, well, then you have a problem, okay? In this case, you will have no solutions, right? This is what is indicated over here. A is equal to 3 and B different from 3, which makes this element different from 0. Well, then you have no solutions, right? Well, if A is equal to 3 and B is equal to 3, then you have 4 variables and only 2 constraints, because the last equation is simply redundant. It's a linear combination of the 2 first constraints. And in this case, well, you have a double infinity of solutions, right? If you stack A is equal to 3 in here, you might see that this is exactly the A matrix of the previous question. And in this previous question, when A is equal to 3, we had seen that the null space has dimension 2. So we'll have a double infinity of solutions. How can you find the solutions? Well, you have to take a particular solution. This is really simple. You take these 2 elements over here and you stack n minus r. N is equal to 4 here, r is equal to 2, zeros below, and then you add, well, the null space. The null space when A is equal to 3, and this from the previous question, question 1, you know that this is this thing over here. So now we have described in full solution the case that corresponds to A is equal to 3, B is equal to 3, where we have a double infinity of solutions. So let us have a look at question 3. An engineer has to calibrate a grammage sensor, and for that he uses foils with known grammage values that are 0, 10, 20 and 30 grams per square meter. When he uses these foils and he measures, well, the grammage, the measurements that are produced are respectively -1, 4, 9 and 14 gram per square meter. The idea is to calibrate the sensor using a span and a bias using the equation that you see on the screen. So how should he proceed? Knowing that he has to perform this operation many times using the same foils, explain and compute the span and bias for this particular example using the most efficient method. As usual, push the pause button and try to do this exercise by yourself. So let us have a look at the solution of this problem. So we start with this equation over here and we replace this one by a vector with the measurements, right? The measurements you find over here. And after span and bias correction, this should look like the values that you should obtain because you know the grammage values of each foil. So 0, 10, 20 and 30. You can rewrite this, of course, in a matrix format like this, right? And the most efficient solution this time is not to use the QR decomposition because, as you can see, even if the engineer uses the same foils all the time, the foils intervene in the B vector, right? Whereas the measurements that you see here in green intervene in the A matrix. So the A matrix will change all the time, right? So it makes no sense to compute the QR decomposition of A. You only do this when A remains the same, whatever the problem, right? So in this case, the easiest solution is to solve this directly without QR decomposition. So what you can do is multiply both terms by A transpose, right? So you have A transpose A times by span is equal to A transpose B. If you do this, you obtain a system of equations, two equations, right? And two unknowns, right? So the easiest thing to do to solve this system of equations is to produce a zero below the pivot over here and to do back substitution, right? If you do this, you obtain a very easy equation to solve. You see that the span is equal to 2, and once you have identified the span, you can easily identify the bias. And here you can see that both the span and the bias are equal to 2. Well, let us have a look at question 4. You have to find the values of A and B for which the matrix is positive definite, and then for the values of A is equal to -2 and B is equal to -2, and these are values that make the matrix positive definite. You have to find the two factorizations of A, R transpose R, one related to the pivots and one related to the eigenvalues. For the eigenvalues, as the computations are a bit difficult, you have to find only the eigenvector associated to the integer eigenvalue and explain how you would obtain this second factorization related to the eigenvalues. As usual, push the pause button and try to do this exercise by yourself. Well, let us have a look at question 4 and its solution. Let us first look at the first part of the question. So, what are the values of A and B that make the matrix A positive definite? Of course, as you know, A is equal to B, otherwise the matrix is not symmetric. So a first prerequisite is that A be symmetric, right? So we'll continue with A over here. One way to impose that a matrix is positive definite is that all its upper determinants are positive. This is certainly the case for the two first, and we have to impose this on the determinant of A, right? So we have to find the values of A that make this determinant positive, right? In order to compute the determinant, it's a good idea to produce a few zeros, and here we have chosen to work with columns, right? So we produce a 0 over here and a 0 over here, and then you can compute the determinant, right? And then you have to, well, compute the roots here, right? Here they are, -1 plus minus square root of 15 over 2, and because of the minus sign here, you can see that, well, the determinant will be positive inside the roots, so we have here a range where this matrix is positive definite. So let's just have a look at the factorization A is equal to R transpose R related to the pivots, right? So we plug in A is equal to -2 and B is equal to -2 in here, and we have our matrix A. So here's our pivot, right? And we have to create zeros below the pivot. It's important here to use this convention with a minus sign over here, and when you do so, well, you will be able to use the multipliers and plug them into the L matrix. If you use this convention to obtain the multiplier, it's quite easy. You take the value to eliminate and divide by the pivot. So you have here 2 over 5. Here you have -2 over 5. If you do the computations, this is what you obtain. Well, next pivot over here, and you have to create a 0 below the pivot. So you use an elementary operation again with this minus convention here. Element to eliminate divided by pivot, so multiplier is -1 over 6. And if you do the computation, you obtain this upper triangular matrix, and that's the matrix U. To obtain L, the lower triangular matrix, well, you plug in the multipliers. It's quite easy. You have used this multiplier to create a 0 over here, so you write this multiplier at the same spot. So here you'll have the -2 over 5, and here the -1 over 6. So you have the decomposition. A is equal to LU, or LD, L transpose. Here D is a diagonal matrix with the pivots on the diagonal. And if you want to obtain a factorization R transpose R of A, well, you can simply write R as a diagonal matrix where you have the square roots of the pivots. By definition, since A is positive definite, these pivots are positive. This is because simply A is equal to -2 is in this range, right? So you can take these square roots, and then you take this diagonal matrix and you multiply it by L transpose. Well, let us have a look at this same factorization, but now for the eigenvalues. We again use A is equal to -2. We have to compute the eigenvalues, so we look at the determinant of A minus lambda I, right? If you write this, this is the determinant that you have to compute, right? And it's always easy to produce a number of zeros. You can do this using this row operation here to obtain a 0 over here, and if you use an additional column operation, you can produce a 0 over here, right? And now we'll compute the determinant on this line. So you have a 1 minus lambda. There's no change of sign because it's second row, second column, times 5 minus lambda times 2 minus lambda, and then minus 0 times -2. Okay, so this is what you have over here. And then we have this additional term. Here we have to change a sign because it's third line, second column. If you add the indices, you have 5. So uneven, you need a change of sign over here. And then we have here 5 minus lambda times -1, so that's lambda minus 5, minus 2 times -2, so it's plus 4. And here you have lambda minus 1 appearing, and you have it over here as well, but with a change of sign. So what you'll do is put 1 minus lambda up front. We compute this thing over here, right? And since we have 1 minus lambda up front over here, we'll have this thing here with a change of sign. So plus 3 minus 2 lambda, right? And of course, you see that lambda is equal to 1 is an eigenvalue, and there are 2 other eigenvalues that are given over here. If you have a look, you'll see that these eigenvalues are all positive, but this is normal because the matrix is positive definite, as A is equal to -2 lies in this interval, right? As requested, we'll only compute the eigenvector associated to this integer eigenvalue. So we have to solve this equation here, matrix equation, where v1 will be the eigenvector. We plug in lambda 1 is equal to 1 over here, and this is what you obtain, right? So what we have done here are two row operations here to produce a number of zeros, right? So it's now quite easy to see that because of this second equation here, that the third element here has to be 0, and because of this last equation here, if you fix the first one to be 1, well, then you need to fix the second one to -2, right? And you know that to compute the R transpose R factorization of A, well, you need the eigenvectors but normalized, right? So here's the normalized eigenvector corresponding to the first eigenvalue. Here, because of these difficult things to compute, right, I'm not going to ask you to compute the eigenvectors of these two eigenvalues, right? But if you could compute them, this is the way to obtain the R matrix in this factorization, right? So you can write A as Q lambda Q transpose. Lambda, it's the eigenvalues, right, on a diagonal matrix, and in Q you have to stack the normalized eigenvectors, right? And to obtain this R transpose R factorization, you can see that you have to take a diagonal matrix in which you stack the square roots of the eigenvalues. This is not a problem. The matrix A is positive definite, so the eigenvalues are all positive, times Q transpose. And this concludes the exam of January 2024.